This is a live video streaming from inside a cement brick building and showing up on my phone outside. And this is the radio carrying it. Two sterile, unattributable, but very Miltech looking devices, a Mohawk camera, Invisio push-to-talk headsets, and sub-gigahertz signal. Trey at MorosX calls this the MX88. I call it the Beast. If a defense contractor made this, it would be a $20,000 line item with a case number and a login portal that probably breaks on Firefox. Trey builds them for people like you, which raises a dangerous question. How much military-style networking can regular builders actually own? So today, I'm taking two MorosX nodes into the field with Trey's partner Hung, along with a Mohawk IP camera and Invisio headsets.
Tim, this is Hung. Ready to check. Over.
I read you loud and clear. Copy, copy. We're gonna find out what they can actually do once distance, trees, and concrete start working against them. A desk test or a perfect point-to-point link across a national park might give you a nice number. This test recreates the conditions military and search and rescue teams might actually face, which is why it matters. We'll test voice, video, and maps through cement structures first, then take the nodes out over distance. The question is whether this inexpensive, open source, cleverly engineered field network can keep useful traffic moving in highly dynamic settings. And the test I'm most excited about is the last one, where we try to carry voice and live video as far as humanly possible with open air, intermittent buildings, and a whole lot of Florida foliage between us. So here are the rules. We start with voice, then we add concrete, then we add video, and finally we add distance. And if the signal dies, we will confess exactly when and where that happened. Honestly, between the push-to-talk headsets and the abandoned dystopian-looking compound that we shot this in, this was probably the most fun I've had recording a video all year. Okay, so round one is voice. The Peltor headset is a great proof point because voice is brutally honest. If the link is bad, you'll hear it immediately. Dropouts, latency, robot voice, etc. So I stayed put on the far side of the first building. Now, this is an abandoned construction site with 3 cement brick buildings, each about 5 floors, including the roof. So not your typical drywall. Okay, so I am on the 2nd floor right now. I'm gonna stay on here for a second or two. Hung just sent some messages and those were getting through, so I think we're gonna be okay here.
Tim, this is Hung. Ready to check. Over.
I read you loud and clear. Copy, copy. Then Hung worked his way through the buildings. In the end, he made it all the way to the far side of the third one. And the audio was definitely still usable. Not studio quality, but adequate for our needs. Okay, so right now I'm on the far end of building 1. Quite a few walls just to get through each building. Hung's at the base of building 2. We have both distance and obstruction, both horizontally and vertically, and we've been communicating just fine. By our count, each building gave us roughly 4 walls of penetration. So by the end of that walk, the signal was pushing through about 12 walls of cement brick, which is definitely not normal Wi-Fi behavior. But let's talk about what is actually making that possible. A few months ago, I reverse engineered a $20,000 class military IP mesh radio using open source parts. That video did very well. Maybe a little too well, but that build was the DIY path. Raspberry Pi, OpenWRT. This is the other path. MorosX is building turnkey MANET nodes, mobile ad hoc networks, which are field routers that create a long-range private IP network anywhere 2 or more of them can hear each other. The promise is simple. Your team gets maps, voice, even video, and the network does not have to care whether a cell tower, an ISP, or some other cloud service happens to feel generous that day. Historically, this capability was reserved for defense contractors. Companies like Silvus, Persistent Systems, L3Harris, and now Anduril have been building this technology for years, but their systems often use licensed spectrum and come with prohibitive price tags. Most don't even bother to show you a price until you fill out a form. MorosX and I take a simpler approach. We put the prices directly on the website. Radical transparency, apparently. Now, credit where credit is due, the military has actually been pretty forward-leaning on some of this less expensive technology. In fact, it was a very influential person in the military military who first encouraged me to talk about reticulum in the first place. And right now, this space is having a moment because small builders are showing up with open firmware, unlicensed spectrum, 3D printed enclosures, and hardware you can actually throw in a bag and take outside. And that's exactly what they're doing. And they're doing it at a tenth of the price of legacy systems. But before we get too deep into the RF, here's what the actual setup looked like. Okay, so we have the MX88 setup, and I have a full push-to-talk headgear audio setup. He has just audio coming through his Android device that's running ATAC. We are on 1 megahertz channel width. We're using the VX plugin on ATAC. But what we're gonna do right now is I'm gonna talk into my headset. It's gonna come out his Android phone. He's gonna have a GoPro on him, and we're just gonna kind of put some range between us, but also put some of these cement walls between us to see how penetration actually works and how many walls we can penetrate with the signals on these devices. Again, he has the same device as me and really the same EUD setup as well, but now we're going to kind of put it to the test here and see what these things can do. Test 1, 2, 3, test.
Yep.
Nice.
Cool. Good copy. Mic check.
Gotcha.
All right, cool. All right, well, I'm gonna go head out then.
All right, sounds good. I downloaded ATAC directly onto an Android phone. ATAC is fully open source, and installing it feels like setting up pretty much any other Android app. Then I installed the VX plugin and connected the phone into the Manet over Ethernet. You could use the node's 2.4 or 5 gigahertz Wi-Fi for that same local connection. For this test, we kept the phone wired into the node. The radio provides the network, while an ordinary Android phone becomes the map, messaging, and voice interface. Then we did the same thing on a second Android device, and that was the extent of our field setup.
I'm towards the end of building 1. I am now in between building 1 and building 2.
So he's at the end of building 1. It's beautiful. Okay, and so we can see the live feed from Hung. I'm in the second floor on the first building. I just wanted to get a little elevated, try to help the signal out a little bit, but we're gonna keep testing a couple things here. You know, most people judge Wi-Fi by 2 things: what generation it is, and really just how fast it goes. But what those systems don't want you to know about is just how much those upgrades forfeit when it comes to range, which is kind of the whole point of Wi-Fi to begin with. I was talking to my friend Firas recently. He builds network penetration tests for some of the largest logistics and retail entities in the world, and the new MCS 13 rates are incredible because Wi-Fi 7 can push theoretical total throughput up around 46 gigabits per second in ideal configurations. But to actually use those top rates, you basically need to be 6 feet from the access point. So speed keeps climbing, often outpacing your internet connection speed, but to attain them, you need to be closer and closer to the access point, which just begs the question, why not wire up at that point with a physical link like Ethernet or fiber, particularly when fiber is becoming easier and easier to string up in home lab settings. But there's a bunch of companies innovating in the other direction, which is to carry usable IP bandwidth across low frequency that can go long range. And Trey says the interesting trick here is not just raw speed, which tops out around 43 megabits per second UDP on the latest Halo silicon, faster than many cellular connections, but it's actually its ability to penetrate dense material, something a lot of other radios just can't do because the channel width is too wide. And this is where the hardware starts to matter. Now, this does not look like a router from Amazon. It looks like something a very competent person built. Big antennas, a 3D printed body, a flywheel battery connector that integrates with mil-spec batteries like the L3 Harris one I have here, field-friendly controls, a headset interface, camera integrations, and that's what I like about it. It still has the soul of a homebrew project, but finally ready for prime time. And if you question the structural integrity of a 3D printed enclosure, keep in mind that this uses a special carbon fiber filament, which is the same material I ran over with my car on the smaller Halo versions, a quarter ton of pressure, and it survived more or less unscathed. But let's take a beat to look at the anatomy of this thing because I don't want it to feel like some great mystery, because it's not actually that complicated. This thing is basically a router running Linux, and in terms of the interfaces, it has a bunch. Ethernet, 2.4 gigahertz, 5 gigahertz, sub-gigahertz, and LoRa. And the beauty is that most of those are bridged. So say you had a convoy with 2 vehicles, each vehicle has 5 people in it and 1 MANA node. Each person could connect to the MANA over 2.4 or 5 gigahertz the exact same way they would connect to a home Wi-Fi router. But through the magic of mesh networking, and because all the radios are bridged, they can also connect to the other vehicle and any other people in that vehicle. And since 2.4 can do a couple hundred feet, they just need to be near their node to access the entire mesh. And to top it off, if you could connect a Starlink terminal or even a cellular hotspot into one of the nodes, then the entire mesh would have an uplink backhaul internet connection, even in the most remote locations. Also, a great complement to this is to run LoRa Sidecar. Now, LoRa does not speak TCP/IP, so it would run as a parallel, redundant, low data transport. But you could use Meshtastic, Meshcore, or even the Meshtastic plugin for ATAC as a backup way to keep basic GPS coordinates and chat comms moving if the IP mesh dropped out, enabling the 2 layers to work together. And LoRa is still the king of range because of its chirp spectrum technique. It can operate below the noise floor, which is something Halo just can't do. Now, that stack is awesome, but our focus today is the Halo transport because it's the piece that most systems still don't have. The Halo radio can support different channel widths all the way from 8 megahertz down to 1 megahertz. And every step down gives up bandwidth, but it also narrows the slice of spectrum that the radio has to listen to, which in turn lowers the noise floor, which improves sensitivity and ultimately gives you more range. But an expert Trey connected me with pointed out that range is only half the story. Every time you cut the channel width in half, the thermal noise floor drops by about 3 decibels. So going from a normal 20 megahertz Wi-Fi channel down to 1 megahertz is a roughly 13 decibel reduction. At the narrowest, most sensitive settings, a Halo receiver can hear signals down around negative 103 dBm. That sensitivity gives you another option. Instead of spending the entire gain on more range, you could transmit at lower power and keep the same useful link. Even in a contested spectrum environment, transmit power is not only about battery life. Every transmission creates an RF footprint that direction finding systems and SIGINT, which is short for signals intelligence, can look for. A 1 or 2 megahertz Halo signal occupies a tiny slice of spectrum and can operate at very low power. That creates low probability of detection and low probability of interception advantages, less energy for an interceptor to find, concentrated inside a much narrower window. And it also changes the jamming problem. A wideband jammer has to spread its power across a large block of spectrum. A narrow Halo channel can fit inside small spectral holes where that interference is weaker. And if you haven't picked up on it yet, this is why fiber optic drones have become more and more relevant. If the command link and video are riding over a spool of fiber instead of RF, there's no radio control signal to jam. Halo is obviously a wireless system, but it's responding to the same battlefield pressure. Keep the link useful when the spectrum is contested. And the sub-gigahertz band is already full of smart meters, industrial sensors, and ordinary telemetry. Halo traffic can blend into that existing RF environment instead of creating a giant, obvious Lobel pattern on tools like Kraken SDR. And that opens up some interesting uses: low-powered drone telemetry, unattended sensor networks, and team intercoms that keep working through concrete and urban rubble. And this is exactly where that contested spectrum argument stops being theoretical. A low-power team intercom is only useful if it can survive the walls, rubble, and any other obstructions between team members. That is why sub-gigahertz and narrow channels matter. And that is the bigger thing that this test is really all about. And if you've ever looked at military MANA radios, MPU-5, L3 Harris, Silvus, and thought, I want that capability, but not that price tag, not that procurement process, and definitely not a black box I'm not allowed to tamper with. This is the fork in that road. Those systems exist for a reason. They throw licensed spectrum, serious transmit power, wide channels, beamforming, MIMO, and deep integrations at the problem. MIMO is in the Halo Spec 2, but it's not implemented in this class of hardware yet. Great gear, but different world. What we're building, Haven and the MX88 that Trey sent us for testing, is for the person who wants field networking that they can actually own. Unlicensed ISM spectrum, no special licenses to operate. The MX88 also uses WPA3 SAE, giving it Type 3 encryption and stronger authentication than the WPA2 security still running on most home routers. And with this, you get a fully open stack that you can log into, mess around with the parameters, and configure to your needs. It runs OpenWRT under the hood, which means it's closer to your home router than to a sealed defense radio. But unlike Ubiquiti gear, you can fork, modify, and extend the firmware because it's open source. Your Android phone does not need a special app or vendor lock-in to understand that it's on the mesh. It just sees Wi-Fi. And we use ATAC because that is useful for this test, but if there's a sufficient uplink, the phone could just as easily use consumer apps like YouTube, voice, maps, video, the stuff you already use, over a link that happens to be bridged across Wi-Fi Halo long haul. Very different than analog radio. You're not renting someone else's network architecture, you're running your own. So why did voice survive 12 walls of concrete? Because we're not playing the same frequency game as the big guys. Military gear often lives higher. L-band, S-band, C-band, wide channels, high throughput, built for serious data rates when the mission supports it. Similar channel width to 2.4 and 5 gigahertz like your home router. Those systems can compensate with more power, better antennas, and additional nodes, but wider channels and higher frequencies still cost you link budget. At the end of the day, we're all at the mercy of physics. But with our nodes, we're playing down in sub-gigahertz, narrow halo channels, lower noise floor, more penetration through concrete, brick, and trees. You give up speed, but you get reach and survivability. For a lot of real-world scenarios, hurricane country, rural property, job sites, farms, hiking, backup comms during outages, or damaged infrastructure, that's the trade you wanted anyway. We're filming on flat Florida terrain about 10 miles inland from the Atlantic. It's a great place for sub-gigahertz RF, but it's also hurricane country, where a private network that survives damaged infrastructure has obvious value. Morse Micro, the company behind the Halo Silicon, ran a field test in Joshua Tree National Park and pushed about 2 megabits per second over 10 miles. And that was a generation behind what's in the Haven 2. And that kind of open, parallel tech stack that puts the power back into the hands of the people is really what this channel's all about. Okay, stepping off my high horse now. So next, we changed the geometry. Hung stayed down on the ground floor and I made my way up to the 5th. Same radios and same push-to-talk setup. But now the signal had to work vertically through the structure.
Okay, good copy. I'm on the outside of building 3, moving to center of building 3.
I got you. Copy, copy. We have floors of concrete. Each building has about 6 walls of concrete. And we haven't had any issues with the comms, but particularly with these walls where like regular Wi-Fi is just going to be blocked because the channel's too wide. And again, it worked well enough to communicate, which makes sense. Usually adding height to the antenna almost always improves Fresnel clearance and overall signal. Okay, so we've proven out voice comms. Round 2 is going to be video. This is the Mohawk camera. Engineered to fit on a helmet or body strap, this IP camera pushes video into rugged elements. For this test, we viewed the RTSP stream in VLC, but in retrospect, we could have pulled that video directly into ATAC using its video integration. But a video stream is harder than voice because it wants more bandwidth. So Hung put on the camera and we ran the building test again. And this is where the network had to carry something much heavier than push-to-talk audio. A headset can survive jitter and signal conditions that will make video fall apart. The camera feed made it through a few buildings, about 2 buildings deep, before it finally cut out. And that was the first real limitation of the day.
Yeah, I copy you. Were you seeing something?
Yeah, so I'm talking to him with push to talk. I got you, copy. But I'm also watching the camera feed.
Tim, Hung, radio check.
Can you hear me? Copy.
Hey Tim, are you talking to me? I can't hear you on the mic. Hey, can you hear me?
But this result is not necessarily the ceiling. There's quite a bit of room for improvement when it comes to these setups. For instance, the Android devices we use saw a Wi-Fi connection. So that means that every app behaved as if internet might be accessible. So background sync, service discovery, and other network chatter can still compete for airtime, even when those requests ultimately go nowhere. For all we know, there were probably dozens of hanging TCP connections trying to egress data while we were running our tests, and that is not optimal. So in the future, a tighter firewall could drop that traffic at the edge and prioritize what actually matters here, which is push-to-talk, ATAC, and our multicast port, and the RTSP camera stream. And we did not do that for this test. As we bake those optimizations into these systems, the same radio link should carry useful traffic more efficiently. You could also imagine borrowing ideas from drone comms, like ELRS-style binding phrases, so devices join the right network cleanly and the system wastes less time on traffic that doesn't matter. Now, we ran this with audio in parallel, and the audio remained intact, which served as a solid fallback. The voice link definitely endured more than the video link, and I gotta say, it felt pretty surreal to watch Hung make his way through the infrastructure and to be able to ask about his progress, but also watch him make progress in real time over the video stream. Running the whole system felt powerful in a way that is hard to explain until you try it. Off-grid, in my control, and very capable. Round 3 is where range and penetration collide. Range by itself is easy to make impressive. You find a clean line of sight, stand on a hill, and that's really it. But how far can we go while the signal is still dealing with real-world obstructions? This was the test I had been waiting for, because now the network has to do everything all at once. So for the final field test, we changed the geometry again. I went up to the roof of the first building, 5 floors in total, and Hung took one for the team and rucked the camera and headset out into the forest in the Florida heat. Between us was an open space, another building, and then a lot of trees. Not a clean range test path or perfect line of sight, but a realistic setting. And we just kept eyes on the Mohawk video stream and kept checking in over comms.
Tim, you still got me?
Okay, so Hung is coming up on like a third or 4/10 of a mile here. He is way out there somewhere in the bush. Yep, I got you. I got the video and the audio.
Our total range before things dropped out was about 640 meters, or a little over 2,100 feet. And that was the best result of the day, because it combined the things that usually fight each other: distance, obstruction, live video, and voice. It also shows why narrowband halo is interesting beyond a simple range test. We carried useful traffic through a small slice of spectrum across distance and obstruction without needing a giant RF footprint or any special licenses. Proof in the field. Now, I want to be clear, I am not claiming that this beats every Silvus persistent MPU-5 or defense radio in every scenario. Those systems exist for a reason. They're optimized for different metrics, including high-stakes environments where lives are literally on the line. This video asks a narrower and, in my opinion, more interesting question. How much of the core capability is escaping that world? And what can we do that they just can't? Private IP networking, voice, video, maps, field range, obstruction penetration, hardware you can actually buy from a small builder. That's the shift. The moat was never only the radio, it was the budget, the access, and the assumption that normal people do not get to play around with this layer. But normal people are playing with it now. Haven proved the DIY path, Morose X is proving the turnkey path, different trade-offs, same direction. And for the parallel stack, this is layer 3, sovereign transport, the part that lets voice, video, ATAC, reticulum, and whatever comes next move over paths you control. And that's why this matters. Not because one box can save the world, because every working link makes the open source, free, permissionless internet we're building a little less theoretical. In this video, we used 2 Manet nodes from Morose X. These are the brand new units ready to take into the field, and you can check them out over on Trey's website. He builds them to order and is just generally super helpful and always innovating in this space. But if you want the DIY path, it's not going to be as rugged, but maybe a bit more extensible. You can check out the Haven 2, which is a guide that teaches you how to build fully digital IP mesh radios that you won't find on Amazon. Open source OS on a Raspberry Pi, a hard-end 3D printed enclosure up on printables, built to go with you into the fray, plus a stack of features we stole from the military, Layer 2 mesh with Batman ADV, the latest long-range Halo radios, and Type 3 encryption, the kind that can't be hacked even if it's intercepted. You don't need any special licenses, and the build costs about 1/10 of what the Pentagon pays for theirs. The schematics are fully open, but if you want to save time, I've been curating all those hard-won insights into my personal builder notebooks. Access is in the description below. But our tests today were not the final say, because I was talking to Trey and he told me that he was able to get over 3 miles with partial line of sight, 1 node in a car and 1 node on the ground, running point-to-point simplex with crystal clear audio. So there's a whole lot more we can do with this technology. There's an old saying in defense engineering: a camel is just a racehorse designed to government specs. That explains a lot, but when you don't answer to a committee, you're free to build what's possible, which today meant carrying eyes and ears through 12 walls of concrete. If you found this useful, check out my video on Reticulum. It's one of my favorite videos on this channel, and I think you'll enjoy it. Thanks.